Sir, kindly carry on your session, sir.
Sure, sir. Thank you, sir.
Ah,
Good afternoon to everyone. Myself, Steve Gneshwar, working as a design engineer in RLE Motors. So today, I'm going to give a comparative study or comparative work of electromagnetic analysis of two-phase flux reversal free SRMs, eco SRMs, and I'll be comparing them with doubly salient permanent magnet SRMs. So the contents of the presentation include objectives, electromagnetic analysis of two-phase SRMs, and their references. Um, SRM are simple motors that are very much uh, simple to operate and very much robust motors. Actually, SRM motors are futuristic motors that could be very much uh, to be a substitute for permanent magnet motors. But the only difference between them is their availability of the motor in the rotor part. Since we don't have any motor in the SRM, on the other hand, permanent magnet motors have more, more magnet in their rotor or other specific parts. The contents that include, um, sorry, the introduction part covers simplicity in the construction, high speed operation, losses, phase windings, more active parts, low inertia. Actually, SRM motor working principle is very much idealistic. They work on the principle of variable reluctance, where the rotor part tends to align in the position where reluctance is very much low and inductance is at the maximum. The main advantages are, as I said you already, the simple in construction, high speed operation, losses are very much low. Well, actually, they in this work I will be comparing the basic SRM with doubly salient motors and permanent magnet motors, where I will be finding them. I will be comparing them in terms of power density and efficiency. So to compare, I have taken two-phase configurations such as 4 by 2, 6 by 3, 6 by 9, and eco SRM. The design steps include design specifications, selection of SRM configuration, and performance of finite element analysis, and finally the prototype testing. So in order to define the design specifications, I need to determine the power and torque required, operating voltage, current, specific speed range, and the first three include the parameters which we will be assuming by ourselves, because the power of the required power rating of the motor should be determined by us. So only we can determine the other parameters. So these are dependent parameters and other parameters are independent parameters. So the motor which we design must be uh, in a position to provide better efficiency as well as the required output. On the other hand, they must be the motor must be with minimum noise and vibration levels and should follow all those safety requirements. So whenever we design a motor for electric propulsion systems, the basic step is to determine their vehicle dynamics. Vehicle dynamics is nothing but the estimation of power that is required to overcome the negative force of the motor. That is, whenever a motor is at rest, it has to overcome few forces from it has to overcome few forces for the motor or the for the vehicle to move from zero to the required speed or the other requirement of us. So to determine it, we are studying about the vehicle dynamics. So let us assume the mass of the vehicle as 1500 kgs, and I will be assuming the velocity of the vehicle to be 100 kilometer per hour. So the constant factor is air density, which cannot be changed. Actually, it is 1.25. So we will be assuming the height, width, and other parameters. Wheel diameter is nothing but the rim diameter. So based on these calculations or these formulas, I will be arriving the power required. So I'll be selecting a suitable SRM configuration based on torque density, simplified construction, high efficiency, control flexibility, and reliability. So main objective of the work includes the electromagnetic analysis with the different flux reversal motors, as I said earlier, the configurations such as 6 by 4 and other configurations. So after which the material properties I haven't included in this slide, so I won't speak about them. Um, so let us see the electromagnetic analysis of two-phase flux reversal SR. So these are the few SRM configurations which I have taken for comparative study. So it includes 4 by 2 SRM, 6 by 3 SRM, 6 by 9 E-core, and double stator permanent magnet SRM. So I will be comparing every motor to obtain the desired results. So I have tabulated the specifications of different configurations. So the motors have been designed for the same power rating, but with different pole arc and stator pole arc or rotor pole arc dimensions. So as you can see that the stack length is kept the same for all the motors. So first 4 by 2 SRM static torque characteristics has been depicted here. So here I can obtain maximum torque of peak torque of 5 Newton meters, but as you can see the dead zone reaching up to zero for all the phases. Okay. Uh, in the while designing the rotor, I can design in both symmetrical as well as an asymmetrical pattern. So it is found that in studies, it is found that asymmetrical rotor have provided better torque characteristics when compared to symmetrical rotor. Okay. For the same 4 by 2, I have designed the rotor as asymmetrical. So I have obtained these results. As you can see that the motor provided better torque characteristics in contrast to the regular rotor. There we obtained the dead zone 0, but here you can see that the minimum torque is near 1.5. So the average torque must be better than the regular one. So the other configuration is 6 by 3. So the flux path is depicted here for the 6 by 3 SRM. So the flux direction, here again I have depicted the static characteristics. The peak torque is less than the previous one. Now for 6 by 9 SRM, so it again the peak torque is around 3.3 Newton meters. Eco. Since this looks very similar to E, so we are calling it as E core SR. This is the flux path obtained. So again, the static characteristics show the peak torque to be around 2.8, 2.6 actually. No, 2.7. Now doubly salient permanent magnet, sir. So in this picture, you can see that the permanent magnet is kept over the periphery of the stator. So whenever we use magnet for a motor, we have to take cognitive torque into account. So this is the flux path visible, flux direction, the stator characteristics. So it is found that the minimum torque it is found to be improved when comparing to the other motors. Improving the minimum torque region will certainly improve the torque characteristics of a motor. So these are the results that are tabulated. So the doubly salient permanent magnet motor has cognitive torque in it, but which is very much minimal in terms of the overall torque value. Also, the ripple seems to be very much minimal. Again, the ohmic loss and iron losses are very much minimal in contrast with the other configurations. So the dynamic analysis was also performed for the doubly salient permanent magnet. So it is found that a torque of around 2 Newton meters, sorry, 1 point, around 1 Newton meters was obtained, which is, this is the torque speed characteristics, which is, sorry. So the torque characteristics show the required torque to be obtained, and it is around 2 Newton meters. So this is the graph for speed and time. So the simulation was run for 100 milliseconds. So it is found to be steady and stable. So this was the prototype developed. As you can see, the availability of the magnet in the over the periphery of the stator. So the cognitive torque was almost the same between the FEA and experimental results. This was graphically drawn actually. The experiment set up for the doubly stator, doubly salient permanent magnet SRM. So I've integrated all the components, and the output was displayed in the digital oscilloscope. So this is the current waveform. So I have compared both experimental and FEA based current waveform. Both are almost identical. So this reveals the reliability of the FEA tool as well as the efficiency of the doubly salient permanent magnet motor. So by assigning permanent magnet, it is found to improve the torque as well as it reduces the loss and other unwanted disturbance in the motor. So the major drawback with this motor is torque ripple and clogging curve. By mitigating it, this could be a better subject for research works. And with this, I will end up the session. Any doubts, you can clarify.
Thank you very much, sir. Am I audible, sir?
Yes, sir. Yes, sir.
Ah, Kana, if there is any doubt, you can raise questions now. Sir, there is one question in the chat box.
Yes, sir.
Sir, the students are asking why we need to prefer switch reluctance motor.
Because it is a bit complex uh, in terms of control. So
Okay.
when compared with the conventional motors that are used in our day to day life, SRM motors are having difficulty in control. So only we are not preferring SRM. Also, more research work has to be carried out in these motors.
Okay, sir. Okay,
Now it
sir.
is yes, sir, yes, sir.
Mm. Sir, any other questions is there? You can unmute yourself and you can ask. Okay, if there is no question, we have some screenshots. So I request everyone to turn on your camera. Sir, Vigneshwar sir, kindly turn on your camera.
Sure, sir.
Ah. Thank you, sir. Thank you very much for your valuable time.
Thank you, sir. Thank you, sir.
Thank you very much. Thank you everyone for attending the meeting. Thank
Thank you, sir.
you. Thank you. Ah.